This is another kind of exercise for the surface integral which is very important. Let S be a closed surface and let R vector be the position vector of any point x, y, z measured from the origin O. Then first we need to prove that the surface integral of R vector divided by R cube dot product with n vector ds is equal to 0 if origin lies outside S. Suppose this is your surface S. If the origin is lying outside of S, then this surface integral is equal to 0. Now inside this surface, R vector divided by R cube is defined everywhere, right? So it is continuously differentiable in this region. And secondly, this surface integral is equal to minus 4 pi if the origin lies inside S. Now if the origin is lying inside S, then at this origin, R vector divided by R cube is not defined, right? It is not defined. So what we have to do is, we just need to enclose this origin O with a small sphere S1, let's say, and let's take V1 be the region enclosed between S and S1, which means now this R vector divided by R cube is defined in this region V1. That means it is continuously differentiable in this region V1, right, which is enclosed between S and S1. Its derivative exists at all the points in this region, right? So before starting up with the proof, the remark is written over here, that is n vector is equal to R vector divided by R. For R vector equal to xi vector plus yj vector plus zk vector, the position vector. I have already explained the proof of this in the previous contents, but now I am explaining this again, the proof of this. We know that what is n vector? It is grad of phi divided by mod of grad of phi, where phi is taken to be as r square. If r vector is this, then what is r square? It is x square plus y square plus z square. This is also very important remark. I have explained this in the previous content at the very start of the surface integrals, right? Please check from there. So n vector is grad of phi divided by mod of grad phi. Let's find out what is grad of phi. So grad of phi is equal to partial derivative of phi with respect to xi vector plus partial derivative of phi with respect to yj vector plus partial derivative of phi with respect to zk vector. So this is partial derivative of phi, that means x square plus y square plus z square with respect to xi vector. And similarly writing for the other terms also. So derivating this with respect to x, we get 2xi vector plus differentiating this with respect to y, we get 2yj vector plus differentiating this with respect to z, we get 2zk vector. That is 2 into xi vector plus yj vector plus zk vector. And this is further equal to 2 into this is your r vector. So grad of phi is 2 into r vector. Now finding the mod of grad phi. So this is 2x whole square plus 2y whole square plus 2z whole square under the root. That is equal to 4x square plus 4y square plus 4z square under the root, which is further equal to, if I take 4 common from this, we get twice of square root of this is x square plus y square plus z square, that is r square. And this cancelled out and we get twice of r. So mod of grad phi is twice of r. So this is equal to 2r vector divided by twice of r. So this 2 cancelled out and we get n vector to be as r vector divided by r. So we have shown that n vector is r vector divided by r. Please remember this. Now let's move on to the proof. Okay, first case is when the origin lies outside the surface S, right? So for that, Let's take V be the region enclosed by the surface S. Now because this origin is lying outside the surface, that means r vector divided by r cube. It is defined inside this region, right? That means it is continuously differentiable inside this region. Its derivative exists at all the points, right? So writing this, then r vector divided by r cube is continuously differentiable in the region V. So therefore, applying the Gauss's divergence theorem, by Gauss's divergence theorem, the given surface integral, this is equal to the volume integral of divergence of this vector, r vector divided by r cube dv, right? So we need to show that this is equal to 0 when the origin lies outside the surface. Now to get this surface integral to be 0, I have to show that the divergence of r vector divided by r cube should be equal to 0. So let's evaluate this. This is equal to the divergence of, writing the value for r vector, that is xi vector plus yj vector plus zk vector. So I can write this as r vector divided by r cube as x divided by r cube I vector plus y divided by r cube j vector plus z divided by r cube k vector. Very fine. Okay. So what is the divergence of this? I can write this as partial derivative of first component with respect to x plus partial derivative of second component with respect to y plus partial derivative of third component with respect to z. So this is equal to denominator square, that is r power 6, the denominator, into derivating the numerator with respect to x, that is 1, minus writing the numerator and derivating the denominator with respect to x. So this is 3r square into partial derivative of r with respect to x. And we know that partial derivative of r with respect to x is x divided by r. You can solve this. And similarly, partial derivative of r with respect to y is y divided by r. And partial derivative of r with respect to z is z divided by r. So I'm using x divided by r over here. So this is x divided by r, and this r is cancelled out with this, and we get 3x square into r. So this is 3x square into r, right? Similarly, by symmetry, I'm writing for the other terms also. So this is plus r cube into 1 minus 3y square into r divided by r the power 6 plus r cube into 1 minus 3z square r divided by r the power 6, right? Okay, we can also cancel 1 r from the numerator and denominator. So this is r square divided by r the power 5 minus 3x square divided by r the power 5. R square divided by r the power 5 minus 3x square divided by r the power 5. Similarly, r square divided by r the power 5 minus 3y square divided by r the power 5 plus r square divided by r the power 5 minus 3z square divided by r the power 5. So this is equal to, this is nothing but your 1 divided by r cube. This is also 1 divided by r cube, and this is also 1 divided by r cube. When adding all these three, we get 3 divided by r cube. And now taking minus 3 divided by r the power 5 common from the rest of the terms, and inside the bracket we get x square plus y square plus z square. So this is equal to 3 divided by r cube minus 3 into, this is r square divided by r the power 5. For r vector to be equal to xi vector plus yj vector plus zk vector. So this is equal to 3 divided by r cube minus 3 divided by r cube. This cancelled out. So these two cancelled out and we get this to be as 0. So we are getting the divergence of r vector divided by r cube to be equal to 0. So this is equal to the volume integral of divergence of this is 0. So which is equal to 0. So we have shown that the surface integral, the given surface integral is 0 when the origin lies outside of the surface S. So this is the case too when the origin O lies inside the surface S. So to apply the Gauss's divergence theorem, we have to enclose the origin O in a small sphere S1 centered at the origin O, having the radius epsilon and lying in S. So this S1 is lying in S. Otherwise we cannot apply the Gauss's divergence theorem, right? Then r vector divided by r cube is continuously differentiable in the region V1 enclosed between S and S1, right? Because inside this region r vector divided by r cube is defined at all the points. There is no origin in this region, right? At this origin r vector divided by r cube is not defined. That is why it is needed to enclose the origin O with the small sphere S1, so that Gauss's divergence theorem can be applied. Right? I hope it is very clear. Both the cases are very clear. Okay, let's move further on. So by Gauss's divergence theorem, the given surface integral over S plus, and we also have to add this with the given surface integral over S1. So this is equal to the volume integral of divergence of r vector divided by r cube dv over v1. Very important. Now because this divergence is equal to 0, we have already shown this. So this volume integral is 0. So this is volume integral of 0 dv, that is equal to 0. So this volume integral is 0. So their sum is equal to 0. Let's take this integral to the other side because we need to evaluate the surface integral for S, right? So this is equal to the negative of surface integral over S1. What is n vector? It is r vector divided by r from the remark. So writing this for n vector. So this is negative of the surface integral r vector divided by r cube, writing the value for n vector as r vector divided by r ds. What is the dot product of r vector with r vector? It is mod of r vector square divided by r the power 4 ds. Now as r vector is equal to xi vector plus yj vector plus zk vector, then mod of r vector becomes, yes, x square plus y square plus z square under the root. And if we take the square on both the sides, we get this to be equal to x square plus y square plus z square, which is in turn is r square. So writing r square for this. So this is negative of surface integral over S1. This is r square divided by r the power 4 ds. That is 1 divided by r square. What is the radius for sphere S1? It is epsilon, right? So this is negative of surface integral over S1, 1 divided by epsilon square ds. We have taken this r vector to be epsilon, so this is 1 divided by epsilon square. Taking this outside of this integral as it is your constant, so this is minus 1 divided by epsilon square surface integral over S1 ds. Now this is your sphere S1 centered at O with radius epsilon. So this surface integral is 4 pi epsilon square, right? 4 pi r square, r is epsilon here, right? So its value is 4 pi epsilon square. So this is equal to minus 1 divided by epsilon square into 4 pi epsilon square. So these two cancelled out and we get finally this to be equal to minus 4 pi. So we have got that. So we have got the result that the given surface integral over S is equal to minus 4 pi for the case when the origin lies inside the sphere S. For the case when the origin lies inside S, right? So we have shown both the results. For the origin lying inside S, we get minus 4 pi. For the origin lying outside S, we get the result to be as 0 using the Gauss's Divergence Theorem. Okay, here ends up the content for the surface integral part 2. Next time we are going to start the new content for the surface integrals, and the content is on the Green's theorem with many assignments and examples. So we start that course next time. Alright, thank you. Stay blessed.